Hello everyone. So in this video we move on through this chapter in differential equations. Part 2, we briefly introduce partial differential equations. Let's make a distinction between ordinary differential equations and partial differential equations. So in this case, a partial differential equation involves derivatives of functions that have two or more variables as opposed to the equations that we studied in the previous sections that had only one variable. In this case they are called ordinary differential equations. Those are the ones that we did in the previous chapter. In this case, partial differential equations, let's here in this little box here we have examples of each. So number one, let's classify them by their order. In this case, this is a first order PDE because if you look at the order of the derivative, the partial derivatives are the first order, the first partial derivative, which is the highest. Okay, so the unknown function in this case, it's going to be one called u that depends on t and x. Okay, so x and t. In this case, the dependent variable is u, and the independent variables are x and t. That is, the variables with respect each function is differentiated with. Like in this case, this function u is differentiated with respect to time or t, and in this case with respect to x. As opposed to this ODE, this ordinary differential equation, in which we have a function y that depends on x, whose dependent variable is y and independent variable is x. And because of the order of the derivative, this is also a first order ordinary differential equation. Now, let's look at another example. So let's look at this big equation. The unknown function, which is the one that is differentiated, it's a u, which depends on, in this case, three variables, x, y, and t. The dependent variable again is u, and the independent variables are x, y, and t. Let's look at this one as well. Another ordinary differential equation. In this case, the unknown function is some n that depends on the variable t. That's all it is. The dependent variable is big N, and the independent variable is t. So in this case, if we look at the highest order of the differential equation, this is second order ODE, and in this case, likewise, the highest order of the PDE is also second order. Okay, now typically these type of equations, PDEs, have that t as a variable because the fact that they have at least two variables, one of the variables has to do typically with the space in which the situation is ongoing, whether this is one dimension, two dimension, three dimension, and then that other variable t, which typically represents time. So typically these processes have whatever area, length, or volume changing with respect to time. So as an extra parameter. Okay, so let's, just the same way we did with ordinary differential equations, let's verify whether a given function is a solution to a given differential equation. What do we do? Well, exactly the same as we have here. All we do is take the necessary partial derivatives and plug them where they correspond on the given PDE in this case, and hopefully both sides of the equation are the same. All right, so let's begin with this one. So in this case, we're given a function that depends on x and t. the partial differential equation here requires one derivative with respect t and another and two derivatives with respect x. Let's go ahead and do that. Okay, so I'm going to write second partial of, first partial with respect t, which is, notice in this case we just differentiate the exponential part, which is going to be negative 8 e to the negative 8t sine of 2t. Okay, so we already got the first derivative with respect to t. Now let's take the two partial derivatives with respect x. In this case, we are going to differentiate only the sine portion because that's with respect that depends on x, holding the exponential just constant. So the partial u with respect x, it will be the derivative of sine 2x. It's going to involve some mini chain rule, and e to the negative 8t times cosine of 2t. But that's not enough. We need a second derivative. Let's take the second partial derivative. Second partial with respect x equals, okay, so this will involve, let me leave some space here. So negative 8t times the derivative of cosine, which is negative sine. I'm going to put the negative in the front of 2. Actually, this is supposed to be x. I made a silly mistake here. It should be x. This also was supposed to be an x. And the 2 from the mini chain rule gets multiplied with the 2 that was already there, plus the minus sign gives us a negative 4. Okay, so let's highlight each derivative with a different color so we can plug in where they correspond on the PDE. So we are going to plug that in here, and we are going to plug this in here. All right, so let me write negative 8 e to the negative 18 sine 2x. That equals 2 times the quantity negative 4 e to the negative 8 t sine of 2x. Okay, so in this case 2 times negative 4, this will give us negative 8 e to the negative 8t sine of 2x rather, not 2t. And the left hand side remains the same. If you notice, there wasn't any change to do there. Okay, so in this case this checks. So this was the second with respect x, this was the first with respect t. So it checks, so that is a solution to the given partial differential equation. Let's do another example. So in this case, u of xt is given as 1 over pi sine pi x sine pi t. Notice the functions, they look the same, however, one depends on x, the other one depends on t. And they're asking us whether this function is a solution to this partial differential equation, in which requires the second derivative with respect to t and the second derivative with respect to x. Okay, let's go ahead and differentiate this function. So partial u with respect t, let's do the t first. That'll be 1 over pi. Sine pi x remains constant because we are differentiating with respect to t. And the derivative of sine here is cosine pi t. So the derivative of pi t is pi, and in this case, notice how this cancel out, leaving us with sine pi x cosine pi t. Okay. So they're asking us for the second derivative. The equation calls for the second partial derivative. So let's take the derivative of this function with respect to t again. The first factor, sine pi x, remains the same because we're differentiating with respect to t only. The derivative of cosine is negative sine, and then times this little pi. I'm going to put it in the front, and I'm going to put the negative from the derivative. Okay, so negative pi sine pi x. Okay. All right, so we are done with the derivatives, with the second partial derivative with respect t. We put it on the left-hand side of the equation. So now let's go ahead and do the partial derivatives with respect x. It's going to work exactly the same. Now we are going to take this factor as constant because we are differentiating with respect to x this time. So 1 over pi sine, actually not sine, this becomes cosine pi x times sine pi t. Okay, so when we differentiate this sine with respect to x, there will be a mini chain rule multiplying by pi right here that actually cancels with the given coefficient we had at the beginning, just the same way with the partial derivative with respect to t. Very similar, this will be cosine pi x sine pi t. Okay, and then we are going to take the second partial derivative with respect to x. This will be derivative of cosine is negative sine pi x sine pi t times the derivative of pi x, which is pi. And there's nothing to simplify here any further. Let's highlight that with blue. Okay, so we are going to plug in this expression here and this expression over here. And do you know it? I think it's not really hard to see that these two expressions match. Negative pi sine pi x sine pi t equals itself negative pi sine pi x sine pi t. So this is as well a solution to this partial differential equation. Okay, before solving partial differential equations, let's represent these given equations in a different notation called operator notation. So what do we mean by an operator? So every time you have symbol, typically symbols are instructions to do on a function. For example, when we see this ddx, this is an operator. This is the operator asking us to take the derivative of the function f with respect x. When we have this when you see this symbol right here, this is the integral operator is instructing us to find the antiderivative or the integral of the function. When we have this big sigma, this is the operator that is instructing us to add all the terms from n equals 1, for example, to some n number of terms. In this case, this is the partial derivative operator. We are going to rewrite it in a more compact form. For example, this partial of the function with respect to x, we just write the partial derivative symbol, and as a subscript, the variable we are differentiating with respect to. Same here for the partial derivative operator with respect to y, just write the subscript and the letter y as a subscript, and when we have the second partial derivative, keep it, and in subscript just write, instead of x squared, just 2x's, and notice how this goes in order. Okay, so let's write this let's write this partial derivatives, partial differential equations in terms of operators. So first of all, I'm going to move everything to one side. By everything, I mean all the terms that have partial derivatives. Okay. And this is what I'm going to do now. So here I'm going to replace, so 7x squared, instead of du partial u with respect to x, I'm just going to write the symbol with an x in the subscript, minus 4 partial squared with respect y and y. And in this case, put everything inside parentheses, write the letter u, which represents the function we're looking for, and let's set it equal to 0, which is the right-hand side of the equation. So in a way, it's like factoring out that u and changing this partial differential, partial derivative symbols into a more compact notation. And in this case, we are going to all this quantity that we have in parentheses, L, call it L, which is the operator, and that's 7x squared, partial with respect x minus 4, second partial with respect y, twice. And in this case, all we do is call this L u equals 0, because this L, which is the operator that is acting on the function u, okay? So this u is this u, and this L, it's all this sequence of operators acting on the function u that checks both sides of the equation. Okay, let's do another example, and in this case we have all the partial derivatives, all the terms that have partial derivative terms on the left hand side. So what we do is 5 second partial t minus e to the tx, or actually 4e to the tx, and partial with respect x. We're done with all this. This is going to be times u. So these operators right here are acting on this given function here, because this term doesn't have, the term on the right hand side doesn't have a partial derivative term factors or anything. All we do is just keep writing it. Okay, so that's all we do here. So let's call this the operator L equals 5 times partial square with respect to twice minus 5, not 5 actually 4 e to the tx partial x. And in this case, we are going to have this operator acting on the function u, and let that equal to cosine of x minus 5y. Okay. Again, we have this u, which is whatever function solves this equation, and L, it's going to be all this right here. Okay. So let's solve basic partial differential equation. What is the simplest partial differential equation? Well, we're looking for some function that when we take the partial derivative with respect t, we get 0. Okay, and we are going to express this as two different functions. You will see. Let me do one case. So what are we going to do? For this simple partial differential equation, we will use a technique of separation of variables that we learned in the previous section. So, partial u with respect t equals 0. I'm going to multiply both sides by t. Okay, partial u equals 0 times partial t. I know what you're thinking. You might want to multiply that by 0. You get 0. That's true. However, I'm going to keep this 0. I'm going to integrate both sides. And keep in mind that the integral is the opposite of the differential, leaving us with a u. And in this case, I can put this 0 outside of the integral to have 0 times the partial of times the integral of dt. Again, this is also inverse of each other, leaving us with t. So u will be 0 times t plus some constant of integration. Okay, let me talk about this constant of integration. So u equals 0 times t, which is just 0 plus c. But 0 plus c is simply c. Okay, now notice this u in the first place depends on x and t. So this u of x t equals, okay, so in this case we did what we call a partial integration. So when we integrate, for example, x to x dx, the integral is x squared plus some constant of integration, whatever that is. It's a number. But in this case, since we are integrating with respect to variables, for example, if I integrate the integral of 2xt with respect x as well, so t remains constant, goes outside of the integral, and we integrate to x dx. The integral of 2x dx will be, again, x squared. Tx squared plus, in this case, I'm not going to put just a number. I'm going to add a function that depends on the variable that was held constant, in this case, some f of t. And that's what are we going to do here. Notice the integration was made with respect to t, but the function we're looking for depends on two variables, x and t. That's what it is assumed. So in this case, I'm going to call this some f of x, just f of x. And that is the solution. I know it's very generic, it's very symbolic, but here, if you take the partial derivative, okay, take the partial derivative with respect t. Do you see any t's here? What do we get if we differentiate something that depends only on x with respect to t? We get 0, and this is exactly what we have here. Okay, so now let's assume, on the other hand, that this function depends not only of x and t, but in this case, if u is some function that depends on x, y, and t, the solution will be the same. U of x, y, t equals some f of x and y, because in this case the integration was done only with respect to t. The other two variables, x and y, were held constant. So in that case, we need to come up with some function that depends on x and y. And again, take the derivative of this function, f of x, y, differentiating with respect to t. There's no t, it's treated like a constant. The derivative of a constant is 0, which is precisely what we have here in the first place. Okay, some partial equals 0. So this is going to make more sense when we solve this partial differential equation here. Partial of u with respect to t equals 4x. All right. So I'm going to use the same technique of separation of variables. Equals 4x. So partial of u equals 4x partial t. Integrate both sides. So don't confuse this symbol right here as with a 2. It's actually the partial derivative symbol. So the integral of the differential cancels. We get u equals the derivative. Okay, in this case, notice this 4x is constant with respect to time, with respect to t rather. Okay, so we simply integrate the integral and cancel with the differential. and we get u equals 4xt plus some c. But again, in this case, the constant is not really a constant, it's a variable function that was held constant when differentiating with respect to t. What do we mean? So this first function that we are obtaining, u of xt, because the partial integration was done with respect to t, the other function remains constant. So that's equal for xt plus some f of x. Well, that is the other variable that remains constant. Now, in the case that u equals some function of x, y, t, just introduce the other variable that was held constant. So u of x, y, t equals 4xt plus f of x, y. Because again, this u was obtained by integrating partially with respect t. Okay, with respect t, so x and y remain constant. Okay, let's solve this one partial differential equation. We use the same technique, separation of variables. So the partial u with respect t equals 9x squared plus 3t squared. This one is going to be more visual, you will see, because now we have something more solid to work with. We have more variables going on, so you will see how, okay, the partial u equals 9x squared plus 3t squared times partial t. And all we do is integrate both sides. Cancel the integral with the differential to get us the u equals, in this case I'm going to have two integrals, the integral of 9x squared partial t plus the integral of 3t squared with respect t. So in this case, keep in mind that we are integrating with respect t. Because we're integrating with respect t, this quantity right here, 9x squared, goes outside of the integral because that doesn't depend on t. 9x squared integral of dt. And in this case, we can just pull out the number 3, the constant, and just use the general power rule to integrate this guy. So the integral of, this is not the number 2, this is the partial derivative symbol. Okay, and cancel out with the integral to get the t. So u equals some and 9x squared t plus 3t squared over 3t cubed over 3 plus some constant of integration. Now we introduce the variables we are involving here. In this case, u is some function that depends on x and t, so u of x t equals 9x squared t. Cancel these guys, plus t cubed plus, well, in this case, since the integration was done with respect t, the other variable will be held constant, has been held constant, I mean. So when we integrate this, we are going to have some f of x. And that is the solution to the partial differential equation, assuming this is but I believe I did a silly mistake here. This was supposed to be cubed, 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 and this was otherwise supposed to be this 3 remains the same. This is 4, and this 3 was supposed to be a 4. Okay, let me change this real quick. 3t to the 4th over 4. Okay, now what if the given function in this case that we're looking for didn't depend only on x and t, but depended on x, y, and t. So in this case, our u of x, y, t equals same function 9x squared t plus 3t to the fourth over 4 plus some function that depends on the variables that were held constant. What do we mean by that? Because in the process of partial integration, we only integrated with respect t. Okay, so in this case, the other two variables x and y were held constant, so we add some function that depends on those variables. Okay, so let's do another one. Okay, partial of u with respect x this time, not t. So notice now in this case the function that we are going to integrate will be integrated with respect x, and we are going to hold t constant. Okay, so let's see how this going to work. So let's separate the variables as we did on the first few examples, and that's plus 5u equals 0. So let me move the 5u to the right hand side. Negative 5u, and I'm going to separate the variables. I'm going to multiply both sides by dx to have du equals negative 5u dx. And then notice this u, I can divide it on both sides to have du over u equals negative 5 dx. So we're ready to integrate this guy right here. So we integrate du over u, which is ln of u, and then the integral of negative 5 dx is simply negative 5x plus some constant of integration. Let me just call it some constant. We are going to introduce those variables in a couple seconds. So to get the u by itself, we need to get rid of the logarithm by exponentiating both sides, base e. So we are going to have u equals e to the negative 5x, and using laws of exponents, this is e to the c. But again, as we did on the previous section, e to the c is just some constant c. So let's call it u equals c e to the negative 5x. Now, let's introduce the variables that we were working with in this case. U of xt, that is u of xt, but because we integrated with respect x, this constant will be some function that depends on t, that the variable this time was switched, the variable that was held constant, and this is simply e to the negative 5x. Okay, now if u was a function that depended on x, y, and t, if u equals u of x, y, t, okay, we are going to have the following then. So we are going to have u of x, y, t. So this f of t will be now an f of y, t times e to the negative 5x. Can we have more variables? Of course, you can make up your own function, like u of u equals, I don't know, some function u that depends on x, y, z, maybe r and theta, and then t. Okay, in this case we only integrated with respect x. Okay, So the other variables will be held constant. So our u of x, y, z, r, theta, t will be okay. We will still going to have this e to the negative 5x, but this will be some f of the variables that were held constant, all this. So some function of y, z, r, theta, t, e to the negative 5x. So you can have as many variables as you want. Just the only thing you need to keep track here of is what variable was being held variable. That is, the partial integration was made in this case with respect x. All the other variables are held constant. Okay, so let's look at another example. Okay, let's look at second order partial differential equations. Well, here we need to play with the notation. So I'm going to write this equation. Okay, I'm going to write this second partial with respect t. Okay, what happens in order to get the second partial derivative of some arbitrary function, of some given function? First, we need to obtain the first partial derivative. Okay, and then to take the second partial derivative, what do? We do this essentially the second partial derivatives. So this is exactly the same in different notation. The reason why I'm changing the notation here is because when I do the separation of variables, is this dt that I'm going to multiply on both sides. That is to start separating the variables. So I'm going to multiply both sides by dt. Multiply by dt. And don't multiply by 0 yet, just the same way we did it earlier. So in this case, cancel dt with dt. And we get d partial u with respect t equals 0 partial t. Now we integrate both sides to get we can get this cancelled, the integral with the partial, to get the u with respect t equals 0 times the integral of dt. Again, this also go away, and partial u with respect t, this will be 0 times t plus, in this case, let me call this C1. The reason why I'm going to call it C1 is because there will be a second constant of integration, because there will be a second, there are two partial derivatives here going on. We do a second partial derivative here. Okay, so in this case, what do we do? So let's, okay, this is du dt equals C1. Okay, let me just call it C1. Let me separate the variables again. C1 dt and integrate partially on both sides. So in this case, the integral cancels the differential, and we get, and that leaves us with the u. And this is going to be C1 times the integral of dt, which is just going to be t plus some C2. What is that C2 going to be? Okay, now that we have it in simpler terms, let's change this and represent them in terms of the variables that we are working with. Okay, so in this case, we integrated partially with respect t. The other variable was the one that was held constant, in this case x. Okay, so how are we going to represent this? So in this case, we are going to have some u of x t equals some c1. In this case, I'm just going to call it f of the variable that was held constant, in this case x times t, plus some c2. In this case, I'm not going to use f. I'm going to use a different letter. Typically, f, g, and h are the ones that are used to represent two different functions. So g of also x, which is all that. Okay. Now, if you take the partial derivative of this, okay, let me do it real quick. The derivative of u with respect to t. Okay, so f of x is some constant, so the derivative of a constant times t is just whatever that constant is. And then the derivative of a constant is 0. And now take the second partial derivative with respect to t. What's the derivative with respect to t of something that depends on x? It's treated like a constant, is 0, and that's how we show that that's indeed a function. Yes, it only has f of x, g of x, and one letter t, but it will make more sense when we do some more examples with actual functions. Like we're gonna do those soon. Now, the other case, what about when our function u depends on x, y, and t? Okay, so u of x, y will be instead in this case f of x will be f of x y times t plus g of x y. Why is that? Because in this case it were both x and y the variables that were held constant during the integration. Okay, so let's highlight this to connect with the other instruction here, and that's final answer for both functions. Okay, let's solve another partial differential equation, but be careful here. In this case, it is first differentiated with y and then differentiated with respect to x. Okay, so the order matters. Keep in mind, as we covered in chapter, I believe it was chapter 8. Yes, it was chapter 8 when we cover partial derivatives. When you see this notation, it means that you do first the differentiation with respect to y, and second you do the differentiation with respect to x. When it comes to the integration, we're going to do it backwards now. You will see how this time we're going to do this first and then we're going to do that afterwards. Okay, first we need to change the notation for this partial derivative. So when we take the partial derivative of a function with respect to y and then with respect to x, we do the differentiation with respect to y first, and then we're differentiating what we got with respect to x, and let that equal to 0. Okay, let's leave that equal to 0. Here I need you to pay special attention to this exercise because of the notation that we are going to use along this exercise. So I'm going to multiply both sides by dx. So this will be d du dy equals 0 times dx. So let's integrate both sides, and integral cancels the differential. Du dy equals 0 times the integral of the x. Okay, so this, in this case, the integral of the differential gives us u dy 0 times x plus some c1. In this case, we do this c1 because we are going to do a second integration, but now with respect to y. So 0 times x is just 0. Let me go up here. So partial u with respect y equals c1. Integrate multiplying both sides by dy, we get du equals c1 dy. y. Then integrate both sides. Let's see, 1 times y plus, you know what, in this case, to avoid confusions here, to avoid going back to many steps, let me call this some f of y. Why do we call this a some f of y? Because the integration with respect, the first integration was done with respect x. We held the other variable, in this case y, constant. Okay, so in this case, we are going to obtain some function f of y. So this partial, the u, let's multiply both sides by dy, f of y, the y, by the way, there I need to change this on the PDF file. It's not going to make too much sense. Okay, the ones that I just circle, I'll explain. Okay, so we integrate both sides. So the integral cancels the derivative. We get u equals some. Okay, in this case, be careful. Notice in this case, we are integrating this function f of y with respect y. So you might remember the notation when we first learned in antiderivatives integration. When we integrate little f, we get big F. We get big F of y plus some c2, but because in this case I'm not going to write the c, in this case I'm going to write another function, call it g, because in this case we integrate it with respect y. We are holding x constant, g of x. So in this case we have some u that depends on actually x and y. Okay, equals f of y, big F of y plus g of x. Hopefully this big F didn't cause any confusions. Again, we got that from integrating with respect, that's a variable over here. Again, this function little f becomes big X once integrated with its same variable. For example, if we integrate g of y with respect y, well, in this case we get some big y. Okay, that's what we get. In this case I'm not going to do a second function. Let's just keep it like this. Okay, now let's solve a couple more examples, and we call it a day for this section. So here, what do we have? If you look at this second partial derivative of u with respect time plus some 9u, this might resemble the following equation. To me, this looks like du dt squared plus 9u, whose characteristic equation is m squared plus 9. One of those equations that we turn into a polynomial equation and then solve the polynomial equation, and then we just write the solution based on the case. So in this case, notice how we are going to get m equals to plus or minus the square root of -9, which is plus or minus 3i. Okay, in this case it corresponds to a complex solution of the characteristic equation in which alpha equals 0 and beta equals to 3. Okay, so what are we going to have? So let's set up the solution as u equals some function well, let not some function, c1 e to the 0x, well, it's actually with respect to t, so not x, actually t0 times t cosine of 3t plus c2 e to the 0 times t sine 3t. Okay, so this e to the 0 is going to be 1. That's 1. That's also 1. So we are going to be left with u equals c1 cosine 3t plus c2 sine 3t. Okay. Now let's introduce the variables that we are working with. In this case, this u is some function that depends on x and t. And notice the variable that is changing in this case is t. And in this case, it is y, I mean not y, it is x, the one that is being held constant. So this c1 will be really some function that depends on x that was held constant times cosine of 3t plus c2, in this case it's going to be some g of x, another function, another c, another function, that times cosine 3t. Now, what if we were looking for some function that depended on x, y, and t? So on the other hand, if u equals some u of x, y, t, this u of x, y, t is f of x, y. In this case, the variables x and y were held constant. Notice when we solved the equation itself, we didn't even mess with the variable x and y, but rather we were looking at the change with respect to t. F of x, y cosine 3t plus g of x, y times sine 3t, which by the way, I need to change that sign over here. Silly mistake again, sine 3t. Okay. All right, now let's look at another example, 2 more and we call it. Okay. Again, look at this type of equation that reminds me of some. Okay, let me write it in a different way to avoid too many confusions. It looks like some u double prime plus 8u plus 25. U prime and 25u equals 0. And this has the following characteristic equation: m squared plus 8m plus 25. In this case, let's see if we can solve this using factoring. So are there factors of 25 that add up to 8? Unfortunately not, so there will be no way around. We will need to use the quadratic formula. So m equals minus 8 plus minus the square root of 8 squared minus 4 times 1 times 25 divided by 2 times 1, 2 times 8. So negative 8 plus or minus 64 minus 100. And then this is equal to negative 8 plus or minus the square root of negative 36. Do you see the negative inside of the radical? That's an indication that we are going to get complex solutions, another complex case. The square root of negative 36, it's going to be negative 6i. No, not negative 6i, actually 6i. We divided by 2, so notice 8 and 60 are both divisible by 2, so negative 4 plus or minus 3i. Okay, in this case, alpha equals negative 4 and beta equals 3. So we are going to called for a solution of the following form: u equals c1 e to the negative 4, in this case x. Notice we didn't use the variable t. Now we're going to go back to x, cosine of 3x plus c2 e to the negative 4x sine of 3x. And well, that's what we learned in ordinary differential equations. Now with the partial equations, we need to introduce the variables that we're working with, x and t. Notice in this case, again, the equation was solved with respect x. Okay, it was solved with respect x. In this case, we held that other variable t constant. So this c1 will become some f of t e to the negative 4x cosine 3x plus c2, which is going to be another function, call it g of t e to the negative 4x sine of 3x. So that's the solution to the partial differential equation. You might want to try it, apply all the in this case the two derivatives. Okay, so now what if we had some u of x, y, t? In this case, again, the variable that we solved the equation with respect to was x. So the other two variables that were held constant were y and t. Just the same here, we had some t. We are going to have exactly the same solution, but the constant, the other functions are going to be some function of y and t. Everything else will look the same. Plus some g of y and t e to the negative 4x sine of 3x. Okay, so that's the solution depending on how many variables. And of course, you might want to have x, y, z, r, theta, t. Just keep in mind that we solve the equation with respect x. The functions f and g would have all these variables. I'm not going to write it. I'll let you do it if you want to explore and expand a little bit. Now, notice in this case, when we solve these partial differential equations, the constants of integrations were functions that depended on the variables that were held constant when doing the partial integration. So we are going to solve this initial value problem, but in this case we are going to do it in an effort to find those other functions that are not necessarily constant, but they're actually functions of given variables. For example, this equation right here. So we have this equation, second partial of u with respect x equals to xy with initial conditions. In this case, the initial condition is that when the original function is evaluated at x equals 0 and y equals y, we get y squared. And on the other hand, when we take the partial derivative, and if we evaluate it at 0, and y, we get y. So I'll show you how it works. First of all, let's solve the partial differential equation, and then we apply this initial condition. So first, let's change the notation to d dx times du dx equals 2xy. Okay, so let's separate the variables in this case. So we separate the variables, and by multiplying both sides by dx, which is this dx right here. So we get partial of d du dx equals 2xy dx. Okay, so let's integrate both sides, but in this case, on the left hand side, The integral cancels the differential, leaving us with du dx equals, in this case, notice we are integrating with respect x. Let me pull this y outside of the integral. So ultimately, what are we integrating? We are integrating, well, I'm not going to write that step in which we pull the y out. I'm just going to focus on the integral up to x with respect x. So the integral up to x is x squared times y that was held constant plus some c1. In this case, this c1 will be our first function. But notice in this case, we are looking for a function that depends on y. Okay, maybe I need to specify this here. U equals some u of x comma y. Okay, so because we integrated with respect x, the function, the extra function that we add here is going to depend on y. Okay, now let's multiply both sides by dx to separate the variables again. Boom, boom. And the u equals x squared y plus f of y times dx. Integrate both sides. Cancel the integral with the differential to get us u equals, okay, I'm going to integrate x squared y with respect x plus I'm going to integrate f of y with respect x. What is going to happen here? In this case, notice I can pull out. Okay, here I'm going to spend one more step to make this clearer. This y goes outside of the integral because we are integrating this with respect x. So we get x squared dx plus, notice in this case we are also integrating with respect x, but this function here is depending on y right there. So I'm going to pull that out of the integral. F of y integral of dx. The integral of dx, what is that going to give us? That's going to give us some u equals the integral of x squared. This will be x cubed over 3 times the y, this y right there. Okay, that was outside of the integral, plus fy times the integral of the x, which is just x, plus some other constant of integration, but that constant of integration will be of the form of g of y. Okay, why g of y? Because again, notice we are integrating with respect x. The other variable is being held constant, and that's something that depends on y. So this is our general solution. Okay, let me call this finally u of x y. Okay, let me call that our general solution. All right, now we need to find the particular solution that involves these two conditions. That is, when we evaluate the obtained function at 0, y, we get 0 cubed divided by 3 times, let me actually, well, I'm going to keep y in blue because that doesn't change. The only one that changes is what is this? The one that changes is only the x. It becomes 0, and that's y over 3 plus f of simply y times x, but in this case, x, what is it? Is 0. So everywhere we see the letter x, we replace with a 0 plus some g of y. Okay, so let me plug in the 0 here. Okay, so 0 cubed divided by 3 is going to be 0. 0 times y, that's going to be just 0 plus f of y times 0. Isn't that another 0? And this g of y is simply g of y. Okay, what are we going to have on the left-hand side of the equation? They're telling us that when u of 0, y, when we plug in 0 and y, this becomes y squared, this y squared that we have here. Okay, so what are we going to have? We're going to end up with y squared equals some g of y. So we just got the first part of the function right here. We put a start. Let me put a star. Okay, we got that. Now we need to find f of y. How are we going to get that y? Okay, so we are going to use the second condition. And that requires, notice, look at the symbol, it requires to work with the derivative. So we are going to take the derivative of the general solution. Let me call it, I'm not going to use the Leibniz notation, the curly D. I'm going to use the subscript notation to make it more compact and to connect with what we have actually. U of 0, no, actually U of x comma y with respect x. So when we differentiate with respect x, y is constant, and the derivative of x cubed over 3, this will be x squared y plus the derivative of f of y times x with respect x. So the derivative of x is 1, then 1 times the constant f of y, which is simply f of y. And then because we are differentiating again with respect x, what is going to happen to this g of y? It's going to go to 0. Okay, so plus 0. Now we are going to use the second condition, u subscript x evaluated at 0 y. Okay, that is, wherever you see the letter x, replace with a 0, y remains the same. And that's how we are going to get the second part of the constant. Okay, so u subscript x of 0y, what is that? Do you see it's this y right here that I'm highlighting again? Okay, so this is going to be y equals 0 squared, which is 0 times y, is simply going to go to 0 plus f of y. This is telling us that f of y equals simply y. All right, now what are we going to do next? So we just got this, let me call this double star. So this will be our double star here. Okay, now we are going to write the particular solution. And in this case, okay, let me go back a little bit. Let me go up. Okay, I forgot another star, I think. 2 stars. Okay, so u of xy equals x cubed over 3 y plus f of y. What is f of y according to what we got? It's simply y times x right here. So it's going to be xy plus g of y, which we got to be this y squared. So notice now how this solution to the equation doesn't have those constants of integration that look like functions now. Now it doesn't have plus some f of y plus some f of x. No, it has actual expressions. Now, if you want to show how this is the solution to the equation, just take the partial derivative of that u of x twice, the differentiating with respect to x twice, and you should get to xy. Okay, so this is all this brief intro to PDEs. Well, actually, this is a really big field of study. If we were to go deeper studying this subject, we would need a more advanced course in trigonometry, a more advanced course in general calculus, like more multivariable calculus, linear algebra, more ordinary differential equations. So in this case, these are just simple cases of PDEs that I thought it was worth looking at. So I'll see you on the next video. Bye.